Okay, so welcome everybody to the ninth APIOS session. Today we will have Dr. Vera Roshchina from the University of UNSW, which will speak about phases of convex sets, dimension, and regularity. So as usual, I would now give the talk to Vera, and please mute yourself and drop your questions in the box chat or wait until the end of the talk, please. Vera, please go. Thank you.
Thank you very much, Giorgio, and thank you very much, Nalini, for inviting me to the seminar. So now I realize that, and for also being welcoming to me to talk about something that is not directly, well, maybe related to the topic of this seminar series. So I hope that you will find something interesting in my talk. And also, because this topic is not kind of a mainstream topic for this group, please don't hesitate to ask questions. So I will be monitoring the chat. So if something is unclear or you just have questions, just write them in the chat. Don't be shy, right? Because I just want to share the joy of my research area and what I do. And yeah, perhaps you will find some of this interesting. So I'm going to talk about phases of convex sets, dimensions, and regularity. So I will just first of all start off with very simple things. I'm going to just talk about convex sets and phases of convex sets. They're just basic definitions in convex geometry and of course in many other areas. Then I will talk about one kind of cute but simple result with my collaborators, predominantly with David Yost from the Federation University, about dimensions of convex sets. I will mention some open problems related to this, and then I will talk about the actual properties of convex cones that help describing the irregular arrangements of faces, especially in higher dimensions, in finite dimensional spaces, but in higher dimensions, dimension 4, and so on, and how we can deal with this and how we can study those properties. So that's going to be a little bit involved, but I hope that for those of you who are completely not in my field, at least some of this talk will be interesting. So I actually uploaded my slides to my site. So I have posted the link in the chat. I think it may be easier for some people to follow if you also have a copy of my slides. Okay, so let me start with just a very simple thing with convex sets. Right, so I'm also only going to focus on finite dimensions, on finite dimensional Euclidean space, and talk about convex sets only, but mostly closed convex sets and mostly compact convex sets, like these ones, like polytopes and the convex sets that you see here, but also in higher dimensions. So just a reminder that a convex set is a subset, in this case, of a Euclidean space, such that if you pick any 2 points in that set, you can unconnect them with a line segment. That line segment will be in the set. So they're sets with no indentations and so on. And even though they look quite simple in 3 dimensions, in higher dimensions, because it's very difficult to imagine what convex sets actually look like, we get a lot of unexpected behaviors and very strange properties, even though they actually look very simple, right? Especially, let's say, topologically, very simple object. Okay, so some examples of convex sets: platonic solids, compact convex sets, Euclidean ball, and tetrahedron, and half of a sphere. You will see why this is relevant. This half of the sphere. It has a very particular structure of dimensions of the faces, and maybe something like this. There's actually, yeah, 2 cones kind of joined together. All right, so what is a face of a convex set? So first of all, faces of convex sets, that they are the main or perhaps the only structural elements that we have at our disposal when we study convex sets. There's nothing else, because convex sets, they're just convex. There's nothing else we can use there. And when we study the structure of the convex set, it's of course the structure of the faces. It's how the faces fit together, how things work between those faces. And if you think about polyhedral sets, polytopes, then of course faces are very natural things. They are the vertices, the edges, the facets, the ridges, which are n minus 2-dimensional faces, and so on. So they are those really structural elements that you can identify in your polytope or polyhedral set. And for a convex set, the definition of a face is sometimes maybe not that straightforward, right? So, but the definition itself is quite simple, but we'll see some examples of faces also. So a convex subset of a convex set, F of C, is called a face of C if for any segment, any line segment in the big set C, such that its interior point is in F, in the subset, the whole segment is also in F. So you can see on those pictures here, which may or may not be confusing or self-explanatory, that if I take, say, a tetrahedron, then, for example, any facet of a tetrahedron, any 2-dimensional kind of surface of a tetrahedron is a face, because, right, whenever I take any point here on this facet, and then I try to find any line segment that is contained in the tetrahedron, the set C, that has this point in its interior, this entire line segment should be inside this facet, right? It cannot be no part of it can be kind of inside in the interior of the tetrahedron. So it's a face. You see from this definition that, say, edges are faces and that vertices are also faces, but in a trivial way, right? You can say that there's no line segment that has this face in its interior that belongs to the set, or you can say that it's maybe just a trivial line segment that coincides with this point. And of course, some general convex subset is not a face because, well, we break this property. If I take a set like this, then and I take a line segment such that this point, for example, is in the interior of this line segment, it sticks out, it's not inside this face, so it's not a face. And something that is not convex also cannot be a face. All right, so let's look at some convex sets. And so, for example, if I have the Euclidean ball, then in 3 dimensions, we're just looking at examples, then for the Euclidean ball, the set itself is its own face. So the ball itself is a face of itself, of course, because, right, all line segments are inside it. And every point on the boundary, every individual point on the boundary is a face. And the only remaining face here is the empty face. There's nothing else. If I look at the tetrahedron, we already looked at it. I have vertices, edges, facets, and the tetrahedron itself. For this set, if I slice the Euclidean ball in half, then every point on the boundary will be a face. The set itself is its own face. And then I have this 2-dimensional face here. And on this set as well, it will be very similar. So I have every point here on this kind of edge, this will be a face. 2 tips here are faces. Every line segment on the boundary like this is a face, and the set itself is a face. And the empty set is always a face, but it's not relevant somehow for what we're going to talk about here. So in principle, you need the empty face to kind of, for consistency and to have minimal faces for maximal faces and so on, but we're not going to talk about this. Okay, so I would like to, before I talk about my results about dimensions of faces, I would like to mention some problems, some open problems that are related to faces of convex sets and that are so simple in their formulation that you don't even need to go into general convex sets. Those problems are formulated, some of them are formulated for polytopes and polyhedral sets. So one of my favorite problems that is related to convex sets and faces is the Zero Conjecture. Zero's conjecture. Maybe many of you have seen that conjecture because the problem is so beautiful and so easy to formulate. And the problem is about nets or unfoldings of polytopes. So if you have a convex polytope, right, it's a set that is defined, say, by finitely many linear inequalities and is compact, or in other words, it's a convex set of a finite set of points, the convex hull of a finite set of points. And if you think about those sets in 3 dimensions, and if you want to make the set out of cardboard, right, so you will cut out some 2-dimensional shape of the cardboard, and then you will fold it, and it will look like your set. Well, that's effectively is a net of the set. So a net of the set is kind of this connected unfolding or development through the edges of the set. So you're only allowed to cut through the edges, or it should be connected through the edges. I mean, I think it makes sense what it really means, right? And then for some convex sets, for some convex polytopes, you have to be careful how you actually cut it to create this unfolding. So for example, here, if you take a shape that looks like a truncated tetrahedron, a little bit squeezed, then depending on how you cut it to create this unfolding, you may or may not encounter problems. So if I look at this shape, then you see that if I fold those 3 kind of edges back, and then I fold this triangle at the top, then I really get this shape. And there's nothing wrong with this unfolding or this net of this polytope. But if I look at this one is problematic. So I didn't cut it properly. And then I cannot actually unfold it in a non-overlapping way. So the conjecture asks if there is convex polytope in 3 dimensions that doesn't have a non-overlapping unfolding. So an open problem, we don't know the solution. And I think the formulation is quite simple. Another one is, I think I shouldn't talk about it too much, is the polynomial Hertz conjecture. And that is related in optimization to linear programming problem and simplex method. So you know that one of the most basic problems in optimization is the linear programming problem. And one of the most basic methods, the simplex method. But we don't know if simplex method can ever be implemented in such a way that its performance is polynomial, that it solves the problem in a polynomial number of steps, where this polynomial should be a polynomial in dimension and in the number of inequalities that defines the linear constraints. The conjecture asks if there is at all a path in a polytope, if you can find a bound for the shortest path in a polytope connecting 2 vertices in terms of a polynomial in dimension and the number of equalities that define this polytope. So even for polyhedral sets and polytopes, there's a lot of open problems that are related to optimization and to geometry of faces that are kind of look simple but difficult to solve. And the 2 remaining pictures here, the second one I'm going to talk about later. I hope I will have time to talk about this picture later. It's related to the Lux conjecture, and this one is related to bodies of minimal resistance. So this is actually Newton's solution to a problem of minimal resistance. So you're given a disk base, and you are told that you want to find a concave function, let's say non-negative concave function, bounded from below by some constant, m, so this is 0, this is m, such that a certain integral is minimized, and this integral corresponds to the resistance of the subject to a rarefied flow of particles, non-interacting flow of particles. And Newton found a symmetric solution to this problem that looks basically like this, a little bit different for different heights. But we don't know what is the non-symmetric one. We know that there must be a convex solution to this problem. We know something about its shape. We know that it should be better than the Newton solution, which is centrally symmetric, but we don't know what it is. And I think one of the problems with that line of research is that we don't maybe have enough tools to describe and study convex sets. We only have very primitive constructions, very primitive ideas related to the geometry of convex sets and the study of the faces of convex sets. Okay. So now let's talk about dimensions of faces. Are there any questions? Anything? Comments? Okay, I don't see anything in the chat. I guess I'll just continue. So I would like to now talk about dimensions of faces. So every convex set has a very easily and very simply defined dimension. So you take the convex set, and then you find the smallest affine subspace, which is just a translation of a linear subspace, smallest translated linear subspace that contains this convex set. And the dimension of that affine subspace is the dimension of the convex set. So because any face of a convex set is also a convex set, Nalini, yes, thank you for your comment. I'm considering convex sets in all dimensions, but only in finite dimensions, only finite dimensional real Euclidean space. But I'm mostly interested in kind of 3-4 dimensional situations, not very high dimensions. So makes sense. I'm going to talk a lot about 4-dimensional sets and so on. So the problems that I mentioned before, they make sense in 3 dimensions. They are open questions in 3 dimensions. The polynomial Hirsch conjecture, not in 3 dimensions. I don't remember the dimension which is relevant, but it's also still rather low dimensional cases that are unsolved. Yeah, it should, yeah, I'm confusing for something else. Yeah, ignore that. So, yes, so now we can define the dimension as of any face as the dimension of that convex set that is that face. So for example, if I take the Euclidean ball, and I think this is somehow complicated, it's somehow complicated for people who don't work in convex analysis, because we always think in convex analysis and convex geometry, we always think about convex sets, and it's difficult to get confused with surfaces and I don't know, some other interpretations. So everything is a convex set. So say for the Euclidean ball, we only have the ball itself, the empty face that we don't care about, and points on the boundary. So the dimensions of faces are 3 and 0. For the tetrahedron, we have faces in all dimensions because we have vertices, 1-dimensional, 0-dimensional, sorry, edges that are 1-dimensional, 2-dimensional facets, and then the tetrahedron itself. There's half of a sphere, again, 0, 2, and 3. There's no 1-dimensional faces. And this funny object doesn't have 2-dimensional faces, but has faces in no other dimensions. So of course, for polytopes, there's nothing interesting about writing down, let's say, sequences of dimensions or dimensional patterns, because all dimensions are always present. So for polytopes, you get everything. If you have a compact polyhedral set, dimensions go from 0 to the dimension of that set itself. And the problem that I would like to first talk about is what kind of sequences of dimensions of faces can be realized in a convex set. And the problem is partially solved, but partially, surprisingly, still open. So think about different objects. For example, think about a polytope. And the polytope has faces in all dimensions. So again, vertices are 0, edges are 1, then we have everything else, then we have ridges and facets, and then the polytope itself. For Euclidean ball, it's another extreme. We have dimension 0, and dimension d, and nothing else. There's no other faces. It doesn't matter in which dimension you consider the Euclidean ball. The only faces are the ball itself and every individual point on the boundary. There are some very interesting examples, very cute examples that are very well known in optimization. For example, the cone of positive semi-definite matrices. I will talk about it more later. So if you're not familiar with the cone of semi-definite matrices, I'm just going to give you this information for now, then I will mention it later. The cone of positive semi-definite matrices is a convex cone. So you just take the space of symmetric matrices and take all matrices that are positive semi-definite. That is a cone, and it's a closed convex cone. So the dimension of its faces come in this very nice sequence, 0, 3, 6, 10, and so on, d times d plus 1 on 2. And this happens because every face of that cone is a low dimensional cone of the same type. So every face of that cone is a low-dimensional cone of positive semi-definite matrices. And then the question is, what can happen in general? So if I write down a sequence of integers, positive integers, find a sequence of positive integers, or even take well, just a subset of non-negative integers, can I always find a convex set that has exactly those dimensions in its faces, such that the faces of that set come precisely in those dimensions? And the answer is yes. And I'm going to show you the idea of a proof. The proof is inductive. So for any sequence, right, I'm going to show you how to do it starting from 0, but you can do it starting from any integer, any non-negative integer. So if you write down the sequence of increasing integers, finite sequence, starting from 0, you can always find a compact convex set that has faces precisely in those dimensions. And the idea is, well, recursive or inductive construction. So what we do, we take a subsequence and then add the next number and the next number and the next number by combining Euclidean balls in a particular way. So the way it works is like this. Suppose that I want to generate a convex set that corresponds to this sequence of dimensions of faces, 0, 1, 3. So I will first generate a set that has this sequence of dimensions, 0, 1. And I have one like this here, right? That's a line segment. So if I just have a line segment and it's a one-dimensional convex set, it has two faces of dimension 0, the tips, and the set itself has dimension 1. And then to add the next number to my sequence, so I'm adding 3 to 0, 1, I'll take the Euclidean ball in the dimension of this number. So it will have faces of dimension 0 and 3. So I embed my line segment in the space of appropriate dimension. I add those things together, those sets together. I compute the Minkowski sum. Right? So the Minkowski sum is just the sum of all points from both sets. And then the resulting object gives me this required dimensional sequence. And then I can do it as many times as I want. So if I'm given a sequence, I will start with the first, say, 2 digits, 0 and whatever. Take the Euclidean ball in that dimension, and we'll keep adding the digits to the sequence. And you see that for this example, we have faces of 0 dimensions here at those tips of the sausage object, and then we have faces of dimension 1 on the boundary, and the object itself has dimension 3. Now, that's not the end of the story, because we have some problems here. I will talk about the particular problem that we have with those sets. They are not facially exposed, but also they're general convex sets, and we want to answer this question for some particular classes of sets. And one kind of set that we want to answer this question for. So what I mean is that if you give me the sequence of non-negative integers, can I produce a convex set that has faces of dimensions that correspond to the sequences and also has specific properties? And that question is not a stupid question to ask, because that question is related to something that we don't know. We don't know for some particular classes of problems, say optimization problems, whether they can be represented by each other, whether they're equivalent or not. And just knowing as much as possible, what can we do with that particular type of objects, with that particular construction? What kind of properties can we encode, or what kind of properties those constructions can have? They're important questions for representations, especially in optimization and for optimization problems. So we can state this kind of problem, for example, for spectrahedra. And remember, I started talking about the cone of positive semi-definite matrices. So a spectrahedron for people working in convex optimization is something like polyhedron, but kind of better. So it's a better thing than a polytope or a polyhedron. It's just a thing that is a little bit more interesting to study. And algebraically, a spectrahedron can be described like this. So you write down a symmetric matrix, and in every entry of the symmetric matrix, you put some linear function on a bunch of variables. Doesn't matter how many variables. So you just put linear functions in each entry of this matrix. So in this case, it's a very simple example. My linear functions are just a constant, x, y, and z, right? So I have 3 variables, so the subject is 3-dimensional. And then you add the positive semi-definite constraint, right? So you say that that symmetric matrix that has linear functions as its entries must be positive semi-definite. And the objects that are defined like this are called spectrahedra. And they are extremely important in optimization because the current paradigm for convex optimization is that if I cannot formulate my problem as a linear programming problem, the next thing I'm going to try is semi-definite programming. And semi-definite programming has a linear objective function and a spectrahedron as the feasible set. So it's the second best thing after polytopes, and it's the second best thing after linear programming, semi-definite programming. So this particular set is an elliptope in dimension 3, right? So it's defined by this particular matrix that should be positive semi-definite. And in fact, if we actually write this object down explicitly, if we want to manually calculate the actual expression for this object, we will use something like Sylvester criterion. So we'll write a bunch of polynomial inequalities that come from determinants of blocks of this matrix, and we'll get this nice algebraic object. So of course, every spectrahedron is, let's say, a closure of an algebraic interior that is defined by some determinantal inequalities that come from a positive semi-definite matrix. And also those objects can be seen geometrically as slices of the cone of positive semi-definite matrices, because if my variables are these guys, right, then if I restrict them to some, if I replace them with some linear functions, it's like I take this cone in the dimension of the entries of the matrix. It's symmetric, so it's n+1 times n on 2. And then I cut a cone, very high dimensional cone, with a linear function. And then I will get that cut, that slice will be my spectrahedron. So I can view this particular spectrahedron, this elliptope, as a cut of a 6-dimensional cone of positive semi-definite matrices with a 3-dimensional linear subspace. All right. So the problem, again, is to prove that for any sequence of dimensions, I can find the spectrahedron that has faces of those dimensions. And I increasingly think, I'll answer the question. I increasingly think that it's actually a simple problem, but several colleagues working on semi-definite programming don't know the answer. I think it's not as difficult as some people think. I think it can be solved by a junior person. Chiang is asking, could the diagonal entries be replaced by another variable? Yes, so this is just one example. This is one pretty example of a spectrahedron. So you can put any linear functions on the diagonal in the remaining entries of the matrix, and you get all sorts of spectrahedra. So it's actually great fun to just draw them and look at them, because they're very beautiful sets. And of course, always convex. And they're convex because they are the intersection of the cone of positive semi-definite matrices with an affine subspace geometrically. So you always have a convex object. So this problem is related to representations, but there are even more interesting problems in representations. So it's fairly simple usually to see if your problem, your practical problem, is a linear programming problem. Whether the optimization problem that we're working with, so I'm always thinking in terms of optimization problem because I'm from optimization, right? If it has a linear objective function and linear inequalities as constraints. And since the second best thing is semi-definite programming, we would really want to have a method that will help us to look at a problem, say a problem that is defined by a bunch of polynomial inequalities, or a problem that has, say, some semi-algebraic set as a constraint, convex semi-algebraic set as a constraint or a feasible region. And we would like to decide if this problem is a semi-definite programming problem. Because if we know that if it's a semi-definite programming problem, then we can easily solve it. There's a lot of methods, there's software already implemented. We know what happens with the duality of those problems. We know how to convert an ill-posed problem into a well-posed problem. We know so much that we really want to, as many problems as possible, we want them to be semi-definite programming problems. So, and then, of course, that's a vague question. Which problems can be represented like this? It's not a mathematical question. A very nice mathematical question is about a specific kind of problem. So you pick a specific kind of problem that you don't know if you can represent, and the expectation is that if we can answer that specific question about that specific problem, we'll understand so much more about semi-definite representation. So this problem that I showed you before, it's a simple problem, I think. This one is very difficult. So this generalized Lax conjecture is a problem that a lot of people in convex optimization and computational algebraic geometry and other fields are trying to solve. There's a lot of progress being made, but it's still open. So we talked about spectrohedra, and now I'm talking about another object, another convex set. And I want to answer the question, can that convex set be represented as a spectrohedron? So we don't know the answer. And that convex set is a hyperplicity cone. It has a very particular definition. So you define it as an algebraic interior, or let's say you define it as a complement of the variety of a certain homogeneous polynomial. Because that polynomial satisfies some properties, it can be shown that that object, that cone, is always convex, which is fascinating because the proof is actually not that complicated. It's like one-page proof. And the question is whether every hyperplicity cone that has this algebraic description can be represented as a spectrohedron. We don't know the answer. We know a lot, but we don't know the answer to this problem. And in a sense, I like to think about this problem as a motivation to what I do, because I think the more I understand about properties of general convex sets, how their facial structure works, and how faces fit together, how I can describe this, I understand I may maybe indirectly contribute to a problem like this, right? To understanding something more concrete, how some whether say, well, I'm not going to solve the Lax conjecture, but that's the direction in which I would like to think, right? That how my research is contributing to the field. Okay, so it's known that in 3 dimensions it's true, and it's true in a stronger form. So you can actually find hyperbolic polynomial that describes this hyperplicity cone that can be explicitly represented as some determinant of the positive semi-definite matrix. And in higher dimensions, it's a little bit more complicated. It's a geometric conjecture, but it's still an open problem. Okay, now I'm going to go back to general convex sets. Now I have covered the motivation, and I will talk about some other results that I'm interested in, and that is something that I'm working on. Are there any questions about that stuff? Please ask questions in the chat, don't be shy. Okay, so now I'm going to go back to general convex sets and talk about some properties of faces without looking at concrete problems and any constructive kind of representations of sets. So one problem with faces is that they may not be exposed. So if you have a polyhedral set, if you have a polytope, say take a tetrahedron, then for every face of this tetrahedron, you can isolate it, or as we say in convex analysis, expose it by a plane, or what we call an exposing hyperplane. Right, so if I have a vertex of a tetrahedron, I can draw a plane that will cut this vertex off this set. Right, if I take an edge, I can construct a plane that basically cuts this edge of this tetrahedron. So every face is represented as the intersection of this original object, the tetrahedron, with a two-dimensional affine subspace. And in generality, in n-dimensional spaces, that will correspond, of course, to n-1 dimensional affine subspace or a hyperplane slicing off those faces of the set. So this works for polytopes, and that's why for polytopes and for polyhedral sets, we can actually define faces as something like that. You can define faces as the objects that you get by intersecting supporting hyperplanes, right? Hyperplanes that have the set on one side with the set itself. But it doesn't work for general convex sets. That's why we have this definition through line segments, and the middle of the line segment intersects in the face, forcing the line segment to be in the face as well. And this is a very classic example from the convex analysis book by Rockefeller, which is like our Bible in convex analysis and convex geometry. And it's kind of a torus, and you take a convex halotest torus. And this is an example of a set that has unexposed. What is a supporting hyperplane? So a supporting hyperplane is basically any, so if you take a hyperplane, it separates the space into two half spaces. So a supporting hyperplane is such that you can fit your convex set entirely in one of those half spaces, non-strictly. So usually the most useful supporting hyperplanes are the ones that actually touch the set, right? So if I have a convex set, then in principle, right, so say on a plane, and then I take any line, right? So this line is such that this half space, one of the half spaces or half planes that it defines, contains this convex set. So this is a supporting kind of line for the set, but it's not very useful. So we would usually talk about supporting lines or supporting hyperplanes that touch the set, right? So something like this is also supporting because this kind of half space contains the set. And of course, the most valuable thing about supporting hyperplanes or supporting planes, lines, and so on, that they isolate some points of the set. So one of the most fundamental results in convex analysis that allows us to do a lot of duality and whatnot is that if I have a closed convex set, then for any point in that set, on the boundary of that set, not on a closed, just for any point on the boundary of a convex set, I can find this kind of a hyperplane that separates this point from the set, right? So that's the basic idea of the separation, and that's the basic idea of having supporting hyperplane and supporting planes and so on. So in this particular case, if I now try to find those supporting planes for the torus, I won't have any problems here. So the faces here on, say, the sides of the torus, they're just points, right? So just singletons. So of course I can support or separate or expose every such face with a plane, right? So I just cut off one individual point with a plane. I can do it with this disk face at the top, right? So I just have this horizontal plane that cuts off this disk, but I cannot do it with those individual points that are also faces on the boundary of the disk. Because if I try to kind of take any inclined plane, then I would chop off too much. I would chop off the whole piece of the torus. So it looks like the only possibility is to have a supporting plane that has one of those top points on the boundary, is to actually have the disk face inside. So that means that those faces on the boundary of the disk, they're not exposed because you cannot isolate them with a kind of a supporting hyperplane or supporting plane in this case. So those points are not exposed. And that creates certain problems in convex geometry. And that's, in a sense, that's the main thing that separates polyhedral sets one of the main things that separates the geometry of polyhedral sets with the geometry of general convex sets. Because say when you think about duality, you don't get those nice duality relations when you construct a polar object, and for every primal face there's a dual face, and there's a nice bijection, and there's nice correspondence in dimensions. You don't get it for general convex sets. So if faces are not exposed, you can get dual face that corresponds to two different primal faces and things like this. So it's a problem, but it also makes convex sets more interesting than just polyhedral sets. Okay. Do I still have time to talk about more things? I hope so. I still have 15 minutes, right? So now I'm going to talk about something that I'm really, really interested in. And it's a little bit more involved than just counting dimensions of convex set. And so here, part of this slide is, so this part of the slide is only related to optimization people. And this motivates what I'm going to talk about from the point of view of optimization. So don't waste your mental energy on understanding those details if you're not interested in optimization. The idea is that for certain optimization problems, oh, thank you very much, Giorgio. Renier asked, there exists an example of a non-exposed face, which is not a singleton point. Oh, let me just scroll back to address this. Example of a non-exposed face, which is not a singleton point. So just answering Renier's question, if there's an example of a non-exposed face, which is not a singleton, I can think about something like this. I can think about, say, a square, a similar example to this torus. I can think about a square instead of the ds on top. And then somehow the rest of the convex face will be like this. So I will attach pieces of cylinders here and maybe take some convex hull of this, right? So in this case, this kind of face, it will not be exposed, but it's going to be one-dimensional. So non-exposed faces can happen in all kind of dimensions. So it's not just individual zero-dimensional faces, non-exposed. All right. So now this motivation for studying nice cones comes from optimization, and so just a general idea of what I have highlighted in yellow here is that for certain optimization problems that are formulated using a conic model, there's different ways of writing convex problems. And if you can write your convex problem in that specific way, which is a conic model, and then that problem happens to be ill-posed, it doesn't have an interior point in a certain sense, you can then reformulate it into a well-posed problem. And that particular reformulation is easy if your cone is nice, if the cone that you use in your constraints is nice. So that's what this yellow thing says. So certain things are reducing ill-posed problem to a well-posed problem is easier using some optimization, using some algorithms, if you have a nice cone. And the actual definition of a nice cone is like this. So you have a closed convex cone. So it's a set that is a cone. So cone means that if you take any point in the set, then if you multiply it by a positive, a positive scalar, then that thing should also be in the cone. So it's only in one direction, right? The cone is just a kind of a positive hull of some set, just a positive cone. It doesn't have to be linear in a sense. And so that's a convex cone. And usually we deal with closed convex cones. And we call such cones nice if the sum of the orthogonal complement to every face with the dual object for that cone, and I will show some dual cones in a moment, or the polar to this cone, is closed for every face of that cone. So it's a weird property, but it's super useful for some applications and for some theoretical studies in convex analysis. So it's just taking it one step further from facial exposure. That is a very classical property. So this is a more kind of involved property that describes or separates good convex sets from bad convex sets, or some sets with good properties from sets with bad properties. And this part here is just some references, right? So it's useful in some applications, just mentioning some applications here. So the most important thing is this. That's a definition of a nice cone. And let me show you how this works. So what does this definition do? And the problem with this is that it's very hard to check and verify. It's an algebraic definition, but it's useful. So what I do is that I have my convex cones. So I have my zero here. Then I take a dual or polar object, the dual or polar cone. So the definition of, say, the polar is all points in my space such that the product, inner product of my points in both cones should be non-positive. I can take a dual cone and it's the reverse inequality, but the main idea is that it's something that should form angle of at least 90 degrees with all points in the primal object. And then I have to verify that for every face of my primal cone, the sum of the orthogonal complement, so the linear subspace, orthogonal to the linear span of that face, with my dual cone is closed. It always works in 2 dimensions, just a picture that shows what we should do to check that this property, niceness, actually holds. And this is an example of a cone that is not nice. So in this case, this particular sum is not closed. So if I take this face, this 2-dimensional face of this cone, so this cone is just an ice cream cone with, say, an additional ray added, and I take the convex hull. So of course this cone is just, it's infinite, it's a cone, and it's convex, so the inside of this cone is part of this cone. Just the picture doesn't look that way. So if I take a 2-dimensional face like this, then I take its orthogonal complement and I add it to the polar of this cone or the dual of this cone, then the sum is not going to be closed. And by summing in convex analysis, we always take sums of individual points on both objects. So if I add every point on this line, on this orthogonal complement to this dual cone, then the resulting object is not going to be closed. Because if you think about it, you're like taking that cone and you drag it along this line. So if you look here, then say this direction will never be in that sum, but will come infinitely close to this direction, right, if we push this polar cone upwards. So that's how this property is broken. And it's a non-trivial thing. It's not easy to actually check this property. And it's not easy to characterize this property. But nevertheless, sorry, it's valuable, and it would be nice to get some properties that are easier to check than checking that some set is closed, especially numerically. I mean, it's not something that can be done. So there was this research by Gabor Pataki from University of North Carolina at Chapel Hill, who kind of started all this renewed interest in nice cones. He has shown that if a cone is nice, then it must be facially exposed. And he also found a condition that you need to add the facial exposedness to show that the cone is nice. And he conjectured that the 2 properties, facial exposedness, so remember when you can slice off every face with a hyperplane, and niceness are equivalent. So in fact, that is not true.
Using balls again? Yeah, she's doing that again. Wat zeiden ze bij de garage?
Ik veel. Hoe bedoel je?
Of de auto op tijd klaar was en zo.
Ja.
Okay, so yeah, so in fact, that's not true. It's only true in 3 dimensions. And the only example, the first example that we can produce that breaks it is in 4 dimensions. So this is an example that breaks this conjecture, right? So it shows that a cone can be nice, but can be not nice, but facially exposed. You have to work in 4 dimensions. Unfortunately, we work with cones, so we always take 3-dimensional slices of the cones to study those properties. And I think I have overestimated my time a little bit. I'm going to skip a few things. So there's some conditions that my collaborator and I found that describe this property as sufficient conditions and necessary conditions. I think I just wouldn't have time to go through them. They all related to tangent cones. And then we have some examples that show that those conditions are not individually necessary and not individually sufficient. There are also examples in 4-dimensional spaces. So we have to, when we draw things, we have to take 3-dimensional slices because nothing interesting happens in terms of those conditions in 3 dimensions. And then maybe I'll just move to the last point, is that the very last thing, the very most recent thing is that, so I was very interested in this property niceness and I wanted to characterize it, and I could only find individual sufficient and necessary conditions, which are very similar. There's some tangential descriptions or tangential relations. One is stronger than the other, but I know that both of them, neither of them is necessary or sufficient and sufficient in itself. And I was very excited when I found this paper by Bruno Lorenzo. He was at that time at the University of Tokyo, producing this very nice condition that you call a closed convex cone amenable if you can bound the distance from every point in the linear span of the face of the cone to the face by a constant times the distance from a point to the cone. I thought that must be equivalent to niceness. And in fact, Bruno has proven that amenable cones are nice. So he has proved it in one direction. However, we have figured out that that property is also not equivalent to niceness. We found a 4-dimensional cone that is nice, but not amenable. So things are only getting more complicated. This is our example. So I'll just spend just 1 minute explaining this, so because I think it's very, very cute. So it's just very cute to look at the structure of 4-dimensional sets and see how we can think about the structure of 4-dimensional cones using 3 dimensions. So in fact, here I have a slice of a 4-dimensional cone, and we construct that example, that 4-dimensional cone, using a 3-dimensional slice. And you see that it has a very funny structure. So we have 2 disks, and we connect those 2 disks with a particular curve. It has a very particular kind of slope in each dimension, or curvature in each dimension. And that particular way that the curve is related to those 2 top and bottom disk faces, it breaks the amenability, it breaks that property that Bruno Lorenzo has defined. But then on the other hand, we can construct a dual cone and take a slice of that dual cone, and that slice is presented here on the second and third picture. And this slice is a polar of the original cone. And we can look at this object and see that, well, that cone is really nice, right? And that this is really a counterexample. And of course, everything can be done algebraically. And I really like this example because in addition to serving to prove that particular fact or disprove a particular conjecture, I think this set has a very interesting structure, because if you look at this tip and then you think about the tangential approximation to this convex set, it doesn't coincide locally with the convex set, but for every individual direction that you take, there is some line segment on which the tangent coincides with the convex set. So I think I should stop talking now. I ran a little bit over the time, but not too much.
Okay, so thanks for the interesting talk. Are there any questions, comments, remarks?
Yes, I would like to have a question.
Sure, please go.
Can we ensure, Vera, that there is not non-exposed phase with dimension 1 less than the original set? I mean, if you have a set with dimension n, can we found a non-exposed phase with dimension n minus 1?
I'm not sure that there's any, I mean, I'm not sure if there's any particular, relation that will tell you something like that, right? In terms of dimensions of faces and exposed faces. I don't think so. I think you can get all sorts of combinations, right, of dimensions of exposed and non-exposed faces or subfaces in a convex set. I hope that makes sense.
Okay. Because if there is not, then in R2, for example, all the cones are nice.
Yes, that's true.
That's true. Okay.
Yeah, that's
okay,
true.
Good. Okay, thank you, Vera. Thank you.
So any other question? Okay, so I've got maybe one question, maybe it's not exactly related to your own work, but I would like to understand if there is any room for applications of this theory to various real-life problems which needs to be treated with optimization and so on. So there might be some, say, visible consequence of these constructions in real-life problems, or is still way too far from.
Yeah, so in a sense, I mean, yes, I think so, but in a sense, it's like real life is lagging behind the theoretical research, because if you have a real life problem, and right, you want to solve a real life problem, you would probably try to relax it or approximate it with something simpler than this. So this is more about theory and what you can do in theory. So the best relation I can produce, right, is through some unresolved theoretical questions that will directly impact the application. So if I can understand more about the facial structure of general convex sets and then contribute to something like a generalized luck conjecture or understanding any other theoretical problems, then that should lead to unified ways of formulating a whole class of optimization problem as another type of optimization problem, for example, right? So to me, the question is just so far removed from the actual application, right, that it's difficult to relate. It's too it's too far. It's too kind of theoretical. But I wanted to say something. Yes, but I wanted to actually make a point that I forgot to make during the talk, is that these days, quite often, those kind of methods like semi-definite programming, they're used to solve pure mathematical problems. And in optimization itself, semi-definite programming is being used to construct numerical methods, to find best parameters, optimal parameters for numerical methods, say for acceleration of some algorithms and things like this.
Can I ask a question, Vera? Going back to what you were describing as the lax conjecture, I presume that's the same lax that we all know in integrable systems community, which is Peter lax.
I think it's the same one, yeah.
Yeah. So you talked about there being matrices of certain types that motivated the start of this theory. I just wondered, is that what he was also motivated by? Looking at classes of matrices, or was there another reason? What was the origin of his conjecture?
It was such a long time ago. I think it somehow came from PDE or something like this, but I'm not quite sure. Mm-hmm. So it wasn't motivated by optimization or algebraic geometry. I think it came from completely elsewhere. And another interesting thing about this lax conjecture is that the original lax conjecture, which is formulated in a slightly stronger form, it was solved by Helton and Vinnikov, who didn't know in the sense that they solved it. So they wrote a very deep paper that solved that conjecture. And then some optimizers wrote another paper in which they explained that, it's like one-page paper, they explained that, well, those guys solved the lax conjecture, but that was about 3 dimensions.
I see. Thank you.
Okay, thank you. Are there any other questions? So if not, I think we can conclude this very interesting session here. And I would like to thank again Vera for her time in preparing and giving this talk. And I would like to invite you to the next talk, which will be in the usual 2 weeks' time, and you will receive the invitation soon.
Thank you very much, Giorgio, and thank you very much,
Thank
everybody,
you.
for inviting me. Thank you.
Thank you, Vera. Bye-bye.
Bye.
Bye.
Thank you very much. Thank you, Vera.